Let's look at the details of the photoelectric effect. Whoops, next page. Next page, next page. There we go. So again, we have a light source which is incident on a metal plate, and that metal plate then will emit electrons which will go across and create a current in the circuit. Okay, so a current, and they're electrons, so actually the official current goes in the opposite direction, but it doesn't matter. There's going to be a current in the circuit. I guess if we want to be really careful, just the current is the direction that positive charges would go. So if negative charges are moving in this direction, electrons, then current officially moves in the other direction. Okay, so that is the photoelectric effect, and then we can do experiments on the photoelectric effect by adding a variable voltage source, which might look something like that. There we go. So that allows us to measure what's called the stopping potential. Okay, so here's remember the issue is that turning up the intensity of the sun, in this case I'm using the sun, a lamp, whatever, turning up the intensity does not increase the energy of the electrons. What it does increase, it still increases the current, but increases the current because it increases the number of electrons as we turn up the intensity. But in order to turn up the energy of the electrons, in order to make the electrons go faster, not more of them, but in order for them to go faster, we have to turn up the color. What do I mean by turn up the color? We got to go from red to blue. As we go from red to blue or infrared to ultraviolet, as we turn up the light going in the direction red to blue, we get more energetic electrons, which can be measured by the stopping potential. So Einstein was able to explain this by giving light, the color of light, and energy. And he maybe, I don't know if we say he copied Planck, but he said that light has an energy which is equal to h times its frequency, right? So, and the frequency is red is lower frequency than blue or ultraviolet, right? So therefore, as we go from RGB, therefore as we go up in frequency, as frequency is increased, therefore energy of light is increased. And that's how we understand it today. But that was not understood, and that's what Einstein proposed to explain the photoelectric effect. And it explained it fully. Let's see how. So Einstein suggested that light comes in these quantized packets of energy, which are equal to hf, and each of those quantized packets is called a photon. So here's the explanation of the photoelectric effect. Quantized packets of light energy called a photon, each has E equals hf. Now what you need to think of here is, in order to understand this, is that this light here is balls of light, right? It's like particles. Here, let me draw it as a different color. There are particles instead, and each of those particles has energy hf. That's a photon. A photon is a particle of light. A quantized packet of light is a particle of light. Each of those has energy hf, and I'm just going to jump ahead. The more of those that you have, you get more by turning up the intensity. You get more of them by turning up the intensity. So you get more of those, and that's why you release more electrons, but not more energetic electrons. In order to increase the energy of them, you have to increase the color of the light. All right, now let's see. Let's go ahead and explain that. So this is Einstein's explanation of photoelectric effect. First, light comes in packets, E equals hf. One thing which I didn't show in the demonstration that Einstein explained is that a certain energy is required to get any photocurrent, any electrons going across that gap, independent of the intensity of the light. So no electrons are released if you use light below a certain frequency. That frequency is called the cutoff frequency, or F0. So therefore there's a cutoff energy, E0 equals HF0, below which no photocurrent will travel. And that's explained by the fact that there's got to be a certain release energy for a given metal. And it turns out that this was material dependent. So this is material dependent, the cutoff frequency. And that's explained by saying there's a certain amount of energy, and we call it Greek letter phi, which is the work function. And that's an energy. The work function is an energy, and it's the amount of energy it takes to release electrons from the metal. and that is equal to HF0. Whoops, that's work function, and that's equal to HF0. That's the threshold energy, also called threshold frequency or cutoff frequency. That's the threshold energy, below which you get no electrons, above which you start to get electrons. Using the adjustable potential difference in the photoelectric effect, you can then measure the kinetic energy of the electrons, or the maximum kinetic energy of the electrons, because they all come off with a slightly different energy because it's a real experiment. That's K max. You can measure the maximum kinetic energy is equal to HF minus phi. In other words, or we can write that as HF minus HF0. In other words, now we're saying that light that is releasing electrons has a certain energy HF. If you subtract the amount of energy it takes to release them from the metal, the rest of the energy goes into the kinetic energy of the electrons, which is now measured in this experiment. We're measuring the kinetic energy by measuring the stopping potential. And that stopping potential, therefore, right, we can do the experiment to show that once we stop it, EVS, where VS is E is the charge of an electron, VS is the potential. Turn up the voltage enough, we get no photocurrent, and we know, therefore, we have now measured the kinetic energy of those electrons coming off of the metal. Or we put these few little factoids together just to have an equation which is sort of describes some part of the photoelectric effect, if you like, which is that. We can measure the stopping potential. We know because of J.J. Thomson's work soon before this, the charge of the electron. We know H is Planck's constant, the frequency of the light, and the stopping potential. So if I'm sorry, not the stopping potential, this is the work function of the metal, how much energy it takes to release an electron. So if we can measure, any two of these things and determine the third. Again, the work function of the metal is HF0, where F0 is that threshold or cutoff frequency. And also, if we might talk about cutoff wavelength or wavelength, and remember that wavelength and frequency are inversely proportional by the speed of light. C equals F lambda. This is the result. But remember the key here, like this is our result, and you might say, so what? It's actually a pretty easy result once you really think about. But once you understand that light has energy HF, and that light comes in these photons, and that what happens is the more photons you get, the more electrons you get, but the higher energy photons you get, the bluer the photons, the higher energy the electrons. Okay, but revolutionary here, remember this was a Nobel Prize, and it did change all of physics for all time from 1905 on, is that light's energy is dependent on its frequency, is dependent on its color, that light's energy is dependent on its frequency or wavelength, right? That light's energy is dependent on its frequency or wavelength, and the intensity just has to do with how much of it you have, but it doesn't increase the energy per photon. And so now when you look at the light spectrum, and this I've sort of implied this a number of times, when you look at the light spectrum, you'll often see the light spectrum drawn like this with increasing wavelength, right, in that direction, and therefore, because of C equals F lambda, increasing frequency in that direction. But now we know that that means that we're increasing energy in that direction, that light becomes more energetic from red to blue or from radio to gamma rays. Gamma rays are the most energetic light, radio waves are the least energetic light. And that also means that often, while you might be used to seeing the light spectrum like this, we often swap places and put gamma rays on that end and radio waves on that end to make energy go up in this direction. Do an example or two just to make sure you understand photoelectric effect. Let's say we've got a potassium surface, and potassium we can look up in a book, has a work function of 2.24 eV. If we shine green light of lambda equals 350 nanometers on it, what is A, the maximum kinetic energy of the photocurrent, right? The electrons that are coming off is called the photocurrent, and B, what is the cutoff wavelength? You'll find that all of these are plug-in problems. You just have to figure out what to plug into. Write down the relationship that if you take the energy you put in, take away the work function it takes just to release an electron, that's the maximum kinetic energy you're going to get out of your electrons. So we're just going to plug into that. HF minus work function, minus phi. H is 6.63 or 6.62, I think 6.63 times 10 to the minus in. Planck's constant, the frequency, well, we're given wavelength of the light that's incident, not frequency, so it's going to be c over wavelength, right? That's the frequency. Frequency is c over wavelength. I guess I could have plugged in numbers. Minus the work function, 2.24 eV. So I should have plugged in numbers there. So it is equal to, plugging in the numbers, and that's equal to. I go on, let's notice a unit thing, so important, and especially in quantum mechanics, but so important in physics in general, units, that we've got energy units of joules here and energy units of EV here. So we do need to remember that there's 1.67 times 10 to the minus 19th. The conversion is 1.67 times 10 to the minus 19 joules is 1 electron volt. And we got to do that conversion. And again, I would convert everything to electron volts so that we end up getting 3.55 eV minus 2.24 eV. So the kinetic energy left for the photoelectrons is 1.31 eV. What is the cutoff wavelength? Well, the cutoff wavelength actually has nothing to do with the wavelength that we're using. We want to know if we turn the light energy down, when will we stop getting photoelectrons? And that's the work function is equal to h times the cutoff frequency, which is hc divided by the cutoff wavelength. You probably caught my error, but this is 1.60, not 1.67. I don't know what I was thinking. I'm a little tired. But what I want to do here is just talk a little bit more about units before I move on, but I don't want to spend any time on it. So just, you can look up or figure out what Planck's constant is in eV seconds instead of in joules seconds. And Hc is also a common constant. So you can often just look up, these are things that you need to have access to. You can look it up or you can calculate it. And Hc is 1.2 times 10 to the minus 6 eV meters, or you can look it up in joule meters. In any case, doesn't matter. Those are just unit conversions, really. And we can go ahead and plug in order to find 1.2 times 10 to the minus 6 eV meters divided by, I'm just repeating myself. So therefore, lambda 0 is equal to 1.2 times 10 to the minus 6 eV meters divided by the work function, which was 2.24 eV. And so therefore, lambda 0, the cutoff wavelength, is 5.5 times 10 to the minus 7 meters, which is 550 nanometers. Nanometers is a pretty common unit for light wavelengths. So that's the answer to part B.